Welcome to the second part of the lecture on challenges and limitations to the network approach and future directions. The second part is on lack of theory building and testing, and I'll probably record it in 3 subparts. I will find out how long this takes. This part is based on a paper I wrote over the last year, but really over the last 7 or 8 years. Everything came together now and it's finally done. I think it's conditionally accepted and should be published in the next few months with the same title. You can find the paper on the slides. I also recently recorded about 60-minute talk on this, which is overlapping with today's talk quite a bit, but it's a little bit more detailed than today. So you can find the full talk and the video online as well. Okay, I see 3 main problems with lack of theory building and testing in the network psychometric world. The first is conflating statistical and theoretical models. I think that's a very big challenge. The second is a problem of latent theories. And the third is a problem of weak theories. And then I will conclude with the section I call Ways to Fix Everything. And before we start this, I want to highlight that I've made all of these mistakes in my career. And I've learned, I could only write this paper because I did this for a few years. And so I'm really not pointing fingers here. Or if I'm pointing fingers at myself and my own work just as much as to other people's work, but I think it's an important issue we need to address. So this is a comic I saw a few weeks ago when preparing for this talk by Mr. Lovenstein. And I took the comic and changed it a little bit. And I think this reflects psychology pretty well. We have a theory, and then our data says no, and then you can see that little researcher being really sad. But does it though? Is it really how we do research? I would say no, it's actually not how we do research. I would say this is the most common scenario, or at least the most benign scenario, where we have a theory and then the data tells us something, but we're not actually really sure what the data tells us because it's unclear what our theory really is and how our data connects to the theory. Right? And then so you see the researcher being left with many questions because the data cannot really inform us about theories if we don't really have proper theories. The second scenario, one of a latent theory, is where the theory is sort of like, you can see it's gray. It's sort of unclear what the theory is. And the data is not informative about the theory, but you can see the researcher smiling anyway. And I think this has happened a lot in social psychology, for example, where people just say their theory is confirmed, but the data really don't confirm the theory. The data are just data, and researchers can argue no matter what that their theory is confirmed. The third case is one of a weak theory, where the theory is really more like a theory. It's not really specified in detail. It has lots of leeway, and again, the data cannot really inform us about whether the theory is confirmed or not, because the researcher can sort of just say, well, but there's a hidden moderator and our theory is confirmed anyway. Here's how I think it should be. I think we should have a strong theory that allows us to bring the data to bear on our theory. The statistical model is an important part of this, which is where network psychometrics comes in this talk. And we will then be informed. Our theory will be wrong, trivially wrong, because it's incomplete. And then we will update our theory, rinse and repeat. Now, after this brief introduction to how I think about theories, let's talk about the last decade of psychological research. I think we've become a lot better at identifying and preventing so-called QRPs, questionable research practices such as p-hacking or harking, where you hypothesis after your data are in, after you've seen the results. And we've become better at doing this, at identifying QRPs with tools like pre-registration, where we write down our hypotheses before we see the data. I have a little bracket here that says, or reflects my thoughts that in the network world, we haven't really done much open science in terms of pre-registration and so forth, because it's been mostly exploratory. And I think we need to do better in that regard. But let's assume for a second that everything is in perfect shape. Everybody pre-registers. What happens? Well, what happens is that the challenges and proposed solutions for these challenges in the last decade have solely focused on improving the replicability of statistical findings, right? So it's all about methodological practices. And in the best case, and that's great, it leads to more robust effects. Effects are great. Psychologists like effects. There are some examples like the Science Accelerator, multi-lab pre-registered replication projects, and so forth. Good team science. But effects still require explaining. Effects are not theories, right? Theories explain effects. And in psychology, we have a lot of effects. As Cummins said, we are overwhelmed with things to explain, but somewhat underwhelmed by things to explain them with. And I think that's very true. And so over the last couple of years, many scholars working on theory formation have argued that there's a crisis of theory in psychological sciences. And after sort of reading up on this for the paper I wrote, I came to the conclusion that the theory glass in psychology is at best half empty. And I really think it also pertains to the network literature that we're part of, that I'm part of. And this is the focus of my talk today. So as you all know, there are two competing theories at the moment. I mean, there are more, but there are two generic competing theories to explain why items of personality scales are correlated, why items of cognitive abilities are correlated, so subtests of intelligence scales, for example, and why items of depression or schizophrenia are correlated, right? And these theories very broadly and very generically are the common cause theory, where you have a psychological construct that causes variation on certain items, observable items. This is not a straw man. This is an actual theory that many scholars in these fields actually hold. Spearman, for example, the sort of the father of the G factor, argued that the correlation among subtests of intelligence can be interpreted as the G factor, and he thought of that as a psychological construct, not as a statistical construct, as a real thing. He called it, I think, mental energy, if I recall correctly. The P factor, in a very similar way, is by some scholars in the field who are very prominent, like Caspi and Moffat, believed to be a causal psychological construct that influences the degree to which people experience psychopathology broadly. This is a quote. And of course, personality traits have been conceptualized in the same way. McRae and Costa, whom you know from the Big Five, for example, very influential scholars, said that personality traits are underlying tendencies that cause and thus explain the correlations among personality scales. I think these are plausible theories, by the way. I don't think that's silly. That's a silly belief to hold. A competing theory that I also find rather convincing is the network theory. You all know what that is. I talked about that briefly, so I'll not talk about this here in detail. And now comes the question, what statistical models we use for theoretical models. For network theory, we often use network psychometric models, the Gaussian graphical model, the vector autoregressive model, the Ising model, and so forth. And of course, for the common cause theory, if you hold this belief that G causes intelligent subscales, you probably, like a confirmatory factor analysis or factor model, is probably a very good model to translate this theoretical model into a statistical model. And so I will talk about network psychometrics broadly today, mostly thinking about the Gaussian graphical model, for example, and about structural equation models today, but mostly about confirmatory factor models as an example of that school of models. Now, when it comes to the conflation of theory and statistics, the first theory problem I identify, there's an inference gap between theories on the one hand and psychometric models on the other hand, right? They're different things, a theory and a statistical model. When it comes to latent theories, the second problem, it's sort of unclear what the theories are. And then why would you use a certain type of statistical model to inform that theory? Or how does it inform that theory? And if we don't know why you use a certain model, how can your model inform your theory formation? For the third point, weak theories, if your theories are unclear, not hidden, not latent, but unclear, if they leave lots of space for interpretation, the theory lacks guidance in informing what model to use, and then in return, it's unclear how the model can inform you about the theory. And I will talk about this in much more detail throughout the rest of the talk. Now, the first part is conflating statistical and theoretical models. And you can see here the little comic where it says, I get confused a lot. Here's a picture of me being confused yesterday. And the other person says, that's not you. And then you can see the guy clearly being confused. And it's sort of me when I read some of the network and also factor model papers. I'm confused. I don't know where the inferences come from. So let me give you two examples. Again, I'm not calling out these authors who are great researchers and in part also friends of mine. So some of the people I call out here are friends, and some of these quotes are from me also. But we need to talk about the problems, and I think inference is one problem in the field. And so here, these authors, for example, say that research into the covariance structure has provided evidence of an overarching general psychopathology factor, the P factor, that reflects an underlying liability to experience all forms of psychopathology. Replication of this factor underscores the importance and utility of transdiagnostic treatment. That's not true. That just doesn't hold. The P factor is well established and replicated, but the statistical model gives us very little information how we should treat people. There's an inference gap in between here. It doesn't work like that. Same for network models. You've seen many papers conclude that because a certain item is central in a network, we need to treat people based on this information. And it's just, this information does not follow, this inference does not follow from the statistical model. It can follow under a set of strong causal assumptions, but if you don't spell out these causal assumptions, your inference simply does not follow. And the problem in these both cases is conflating theory and statistics. And to be fair, that's easy to do in psychology because we use the term model both for statistical models and theoretical models. So one takeaway from this lecture is if you use the term model, ask yourself, what do you actually mean? And here comes the sort of thing that blew my mind a few years ago when I noticed that network theory and the common cause theory in their most generic forms are competing theoretical explanations. Both cannot be true at the same time, at least in this generic form. But network psychometric models and factor models are, at least under some conditions, equivalent. They have equal fit to data. And now this is a bit of a white lie, and Riet van Bork and colleagues have done more work on this. So if you want to know the details on this, I recommend reading her recent paper at the bottom, link to. But in general, this holds, and I want to give you an example. So in my paper, what I did is this is called statistical equivalence in the literature. Ignore the text here. I simulate data from the left network model. So the left network model is the true model now. I simulate data, and then I fit the right network model to it, and you get perfect fit. And vice versa, if I simulate data from the right model, the factor model, the unidimensional factor model, and I fit the network model on the left side to it, I get perfect fit. And that means you cannot conclude from a statistical model in this sort of data what the data generating mechanism is. And that also means that your inferences don't follow without strong assumptions. Now, to be fair, interventions can help us figure out what generated the data to a degree. Because if I would causally intervene on X1 here, let's say that's sad mood, and I have an intervention that actually works really well, sad mood intervention, and I see that nothing else changes, no other symptom changes, well, I have an indication that the right model might be the data generating model, or at least a model of the right side. I mean, there are variations, of course. But if I intervene on X1 and many other variables change, I conclude that X1 probably has some causal impact on the other variables in the system, and maybe a network model may be the underlying model. Now, I'm simplifying things, of course, but in principle, interventions are the best way around statistical equivalence. Conclusions: model fit tells us very little, and in some cases nothing, about mechanisms that generated our data. A well-fitting model cannot be taken as evidence. A well-fitting factor model cannot be taken as evidence that P or G exist as psychological constructs, or that it causes the data. And likewise, a network model cannot be used to tell us where we should intervene on a system without very strong assumptions, at least in present data. Right? This is the inference gap I'm talking about. Now, I want to give you a few examples in the network literature where I see this conflation happening regularly. And the most common one, or the most sort of obvious one, are DAGs. Now, if you read network theoretical literature, people argue that vicious circles, so causal feedback loops, are at the heart of network theory. Conditions are maintained by feedback loops and vicious cycles. And if you are a therapist working with CBT or other therapeutic approaches, you probably believe this is true to some degree, right? Some therapies are about breaking vicious circles. That can be between problems or between symptoms or between the environment and the person. But now, in recent years, it has become more common to fit directed acyclic graphs on cross-sectional data. So these are directed graphs that are acyclic, and that means if you start at a certain point, you can never go back to that point. They forbid feedback loops in cross-sectional data. And I don't understand, but the scholars who write that sort of work often don't grapple with that problem. If network theory has feedback loops and your statistical model is unable to model them, how can your statistical model inform us about the theories? A second point is that there's a recent paper by Jonas Hasselbeck and colleagues who showed that some of the most common network psychometric models are unable to retrieve core processes that we think network theory proposes as part of the data generating mechanisms. But if our models cannot retrieve these mechanisms, why do we use these models? I already talked about node centrality, so we can skip that here. And of course, I also talked about between-person models and within-person inferences. It also fits this inference gap here. That doesn't follow. Brief summary: results of statistical models are taken to corroborate theories, but they ignore the inference gap. And the most common shortcut in the literature is to interpret the statistical model as a theoretical model. And that's a huge problem, I think. Importantly, all of these challenges hold irrespective of the quality or the quantity of the data. And that's a point I really want to stress. It doesn't matter how well you measure something. You cannot escape statistical equivalence. It's in the data no matter what you do. And so we need to think about theory a little bit more. That was the second part of the lecture on challenges of the network approach. I'll be right back with the third part.